So what are we going to talk about? Well, the title of the lecture is called the Astronomer's Toolbox, but I think Toybox is really the better analogy, at least in my mind. Really, because these are the instruments or toys that astronomers use in order to understand the universe as we know it. And so I'll be talking about telescopes and detectors for the most part. After that, I will be talking about actually, well, we'll see. Let's just get into it. So, the telescope is the main tool that astronomers use in terms of collection of data. One could argue that the computer is actually the most powerful tool in a astronomer's arsenal because it is what allows us to interpret the data that is collected by said telescope. In specific, a telescope only has really one purpose, and that is to gather light along all wavelengths. Because as I mentioned in a previous lecture, 95% of astronomical knowledge is derived through the study and analysis of light. There are, roughly speaking, two types of telescopes. There are refracting telescopes and reflecting telescopes. And both of them were actually developed fairly early on, although the refracting telescope is probably the most famous one because of Galileo's contribution to it. The refracting telescope was actually the first to be developed by Hans Lippershey in 1609. So Galileo did not, in fact, invent the thing. He simply was the first
Um,
person documented
it's
to
been at
actually
8 minutes for the past 10 minutes.
look at. He was actually the first person to look at the night sky with it. He's also the first example of the uh, close working relationship between astronomy and the military, because essentially he got funding for his telescope, or at least as the story goes, he got funding for his telescope by going to the Duke of Florence. I actually don't know, the leader of Florence. And in order to justify the amount of money he was asking for, he said, well, this telescope not only just looks at the stars, but also can be used to look for uh, invading armies before you can actually see them with your naked eye. And so apparently that was the main selling point. Speaking of the naked eye, the first instrument that was ever used for astronomical work, of course, was the human eye. The human eye is a refracting telescope in the sense that a refracting telescope uses lenses to bend light to your eye. Last lecture, I talked about the concept of refraction, and essentially that's the idea that as light passes through different media, it actually gets bent by a certain angle as it passes through. So the eye is a perfect example of a complete telescope system or an optical system in that it includes a very rudimentary telescope, the lens of the eye, and a detector, the retina on the back end. The optical nerve, you can think of that as the USB cable to take the information collected by the retina uh, and transport that to the brain. The eye, of course, has certain problems with it, and those problems, namely, are in the ability of or the amount of light that it can actually collect, and something known as angular resolution. Now, the eye does have some perks that current, even state-of-the-art detectors do not have, and I'll talk more about that later, but there's something called dynamic range. There's something called basically the ability to see something that is very bright against a very faint background, or vice versa. The eye is still the best instrument that we have um, for seeing those sorts of differences or that sort of range. Now, I mentioned angular resolution. What is angular resolution? Angular resolution is the minimum angular separation between two objects where a telescope can distinguish there are, in fact, two separate objects. Now, if you're a fan of driving long distances like I am, and you do it at night, you may have encountered this situation where You look in the rear view mirror, and behind you, you see a single light, or what appears to be a single light. And then slowly over time, as that vehicle gets closer and closer to you, you notice that that single light basically expands into two headlights from a car. Now, while uh, the headlights have a fixed linear position, meaning they're only roughly what, a meter and a half, maybe 2 meters separated from each other, they can appear to be closer or farther away from each other based on how far away that object is. So, for example, for the woman on the right, the angular separation or the distance, the apparent distance between those two headlights is much smaller than the angular separation between the two the man sees on the left. Now, angular separation is, or angular resolution rather, is a rather fair, is a fairly simple relationship to figure it out. So in this strangely worded equation, basically the limit or what's known as the diffraction limit of a telescope, the smallest angle that the telescope can distinguish as two separate objects, is equal to some constant times the wavelength of light that you're looking at. So, for example, in the visible range, you're talking about 400 to 700 nanometers. In the radio, you're going to be talking about centimeter length or even meter length wavelengths. And then finally, they're divided by the diameter of the telescope. In astronomy, bigger is in fact better. Here, you can see that this is an inverse relationship. And with angular resolution, again, this is the limit. So this is basically how close two objects can be in the night sky for us to be able to tell the reality that there are two objects there. Also, you can look at it in terms of the amount of detail that you can see. For example, I often get asked at our telescope, can I see the Apollo moonlander? The answer to that question is no. The telescope doesn't have the angular resolution to distinguish something so small on the lunar surface. Now, if I had a giant telescope, then things might be different. But, and I've actually never calculated how big a telescope you would need to do it. Anyway, so you want that number to be as small as possible. The smaller that number is, the more detail or finer detail you can distinguish in an astronomical object. And so again, this is a inverse relationship with diameter. The larger the telescope, the smaller the angular resolution limit that you get. We're going to return. We're also going to return to this idea that, or the fact that this is also wavelength dependent, meaning that the smaller the wavelength, the smaller the angular resolution. So in terms of people who look in the optical or IR, like I did for my research, if I have a certain telescope of a certain size, my angular resolution is far better than if I were to go to the radio, because the radio wavelengths are orders of magnitude longer than they are in the um, visible. Hence why when we see when we see when we talk about radio telescopes, you'll get an idea of why they're always so large. Um, so yes, because of well, let me get through angular resolution and then um, I can answer that question in terms of how far can you see? That is a function of how much light you can actually collect. Yeah, same logic. Basically, yeah, camera is just again is a optical system. You can think of a telephoto lens as the telescope and the CCD or the detector in the camera or film if you like older style photography or photographic film photography, that is the detector. So again, here's an example of what I mean by angular resolution. So On the left, you have kind of the theoretical. If you have two objects of a linear distance and you have a telescope of a certain size and you know the wavelength, then that's basically what the two objects would look like. Um, Now, on the right is an actual lab setup where you have two lights that are at the back end of an optical bench, and you have a telescope that has an aperture to it. So you can make the size of the telescope smaller, and then as you
Oh
make the
shit.
aperture larger,
Sorry.
That's fine.
you can when you make the aperture larger, you can effectively make a larger telescope. So as you increase the size, those two objects first start off as a blur. Basically, you can't tell where one object starts and the other object stops. And then as the gets larger, that object or that light source becomes more of peanut shaped. And then finally, if the telescope gets large enough, you can actually resolve the two objects as separate. Now, I found that there can be a no whenever if we ever have virtual classes again, anytime we have virtual classes, I'm not going to have in-class questions. Um, that is difficult enough in the lecture hall, and I don't know how it would work um, virtually. So, or at least I haven't tested it, and I don't want to test it now. There is a I've talked to some people, and there is something of a misconception when it comes to angular resolution. Uh, the angular resolution is not really related to whether or not you can see the object. It is to a certain extent because you can see from the actual that if you look at the total amount of light or the brightness rather of the objects, uh, as the objects get fuzzier and fuzzier, overall they get dimmer and dimmer, and so that's going to affect your ability to see it. However, resolvability does not mean is not really related to detectability, meaning that if you're looking at an unresolved object, like the top of like A in the actual, that doesn't mean you can't see it. You still have light coming from those two stars, but you cannot distinguish where that light is coming from. Uh, Excellent. Thank you, Andrew. All right, so to the question of how far you can see, that is directly related to light collecting area. And that is simply a function, again, of the diameter of the telescope squared. So the larger the telescope, if you double the size of the telescope, you now have four times as much light collecting, or you're collecting four times as much light as the other telescope. So for the human eye, under the best conditions, um, the human eye dilates to around 8 millimeters. So here, the human eye can only collect a fairly small amount of light every second in comparison to the telescopes that we use today. And so that is why when we look up at the night sky, uh, we can we can only see relatively small section of stars. Uh, a person or a colleague of mine would told me that when you look up at the night sky, the stars that you are seeing are all superfluous in one form or another, meaning that they are all very intrinsically bright or all very close to us. Because the stars that are not intrinsically very bright or the stars that are far away, our eyes don't have the light collecting area to detect it. There's a question as to, all right, where is the homework posted? And that is SmartWork 5. We can talk about that at the end of the class if you need to. So, all right. One of the other things that I get asked when people visit the telescope is the magnification of the telescope. What is the maximum magnification that you can achieve or that we can achieve with the telescope? And when you are buying inexpensive telescopes, say at Walmart or any kind of retail store such as that, you'll see they'll plaster like 150 times magnification on it. As I'll talk about later, magnification is something of a misleading quality in that the more the magnification, the a larger magnification does not necessarily mean a better image. Really, what is at play, or really what the best the the better quality to look for is angular resolution. What is the finest detail that the telescope can see? But if you were wondering how to calculate the magnification, then you would need to simply calculate the focal length of the telescope divided by the focal length of the eyepiece. And in a couple of slides, I'll uh, tell you what term the focal length means. Now, optical telescopes, refractors. What is the definition of a refractor? Really, like I said before, a refractor is a telescope that uses lenses to bend light to a focus, to either your eye or to some kind of uh, detector of one sort or another, be it a photographic plate or a digital camera or what have you. Another term that I'm going to be using is aperture. Aperture is the the effective size of the telescope. So for example, I will refer to our telescope as a 32 inch. 32 inches refers to the aperture of the telescope. In regards to a refracting telescope, that number corresponds to the diameter of the objective lens. That is the first piece of glass that the light hits in the telescope itself. So that would be the lens at the very top of the telescope. The image that you're seeing here, for example, is the 1 meter is not really accurate. The um, the telescope that you're seeing here is the 60 centimeter telescope at Yerkes, meaning that the lens at the top of the lens at the top of the telescope is actually 60 centimeters in size. Yeah. Here we go. Focal length. Focal length is the physical length between the distance from the objective lens to where the light comes into focus. Comes into focus. So that is where the light comes into focus. That is where you would want to put your eye or your detector, and that is known as the focal plane. And this is a couple of examples of different sizes of focal lengths and where images, light from stars, would be displaced on the image. Thing that you see here, the thing that I want to point out here is with a refracting telescope, if it's just a simple refracting telescope, then the image that you're going to see through a telescope is going to be inverted. So if you wanted to take a telescope that was designed for astronomical work and try to use it for bird watching or anything else, you're going to be kind of stuck in the sense that anything you look at on the Earth is going to be flipped over. So things like stars or planets or whatever, or vertical orientation is really not a necessary. It's not necessary. We don't really care about that. So just be aware that if you try to use a telescope uh, that is meant for the sky on the Earth to anything on the Earth, then you probably will run into that problem. So, why don't we use refractors anymore? Or at least from a research standpoint. When you look at all of the modern telescopes that we have today, from Keck to Gemini to Hubble to JWST, all of these telescopes are reflecting telescopes. They use mirrors. Well, there are a couple of different problems. The first one, which is actually something that can be mitigated, is something called chromatic aberration. As we saw with the prism, the wavelength of light determines how the angle of how far it's bent. Basically, that creates a dispersion effect or a prism effect. And so this is using lenses. So refraction is at play, and so dispersion is going to be at play. And so what we find is that very close to the star, you'll have it be white or its true color, and then you will get a rainbow pattern of colors emanating from it that are simply due to the refraction. They're not due to any sort of astrophysical problem. But again, that can be corrected for using a different combination of lenses. The real problem with refracting telescopes is an engineering one, in that, generally speaking, the focal length of the telescope is scales with aperture, meaning that if you have a larger aperture, because we want to build the largest telescopes we possibly can because we want to collect as much light as we can to see farther and to see more detail. So again, if you as you build up the aperture, the focal length gets longer and longer, generally speaking. So this is a 60 centimeter telescope, and you can see how very long it is. Over to the left, you can see the lower image over to the left, there's a dude in a blue shirt. And so that gives you a sense of scale of just how immense this telescope is in terms of its length, in terms of its focal length. And so from an engineering standpoint, that is the largest telescopes we have now are 10 meters. So uh, I can do math, a thousand centimeters. So we're talking about 10 or basically an order of magnitude, 10 times the size. So you can imagine that tube is going to be roughly 10 times as long if you were going to put a 10-meter lens on the top of it. So trying to support that whole thing is going to be a Herculean effort from a structural standpoint, because you need that tube to be perfectly straight. If the optics are misaligned, that is going to cause a lot of artifacts in your image that are going to be problematic when you try to study them, when you try to study the data or extract data from it. The other problem is simply gravity. So a lens is big in the center, and then it tapers off towards the edges. Typically, a convex lens, that is the case, which is what typical um, refractors use for their objective. So it's sort of diamondy shape, kind of like this. So most of the mass of the lens is located at the center, but because you need the light to pass through the lens itself is supported by the edge. So if you have a large enough mirror or a large enough lens, you have a lot of glass in the center. You have a lot of mass in the center. And if you're looking up, then gravity is going to pull down on the center more so than it does on the edges, and the lens, after a fairly short period of time, is going to deform. And again, that's going to create artifacts within your image, which makes it difficult to get precise data from those images. Excuse me. Dealing with a sinus infection. Not that you really needed to know that, but anyway. So that's a main reason why modern telescopes today are not refractors. Instead, they are reflecting telescopes, meaning that they use a mirror to redirect, to basically reflect or bounce the light from the top of the telescope uh, to the bottom. The light travels from the top of the telescope to the bottom, gets reflected off of a mirror, and then in one way or another, that light gets redirected to a position that is more convenient. Uh, so if we look at three different types of reflecting telescopes. Because unlike refracting telescopes, where you're basically just stuck with one optical layout, comes in, hits the objective lens, gets refracted down the length of the tube, and then uh, gets imaged on the focal plane or comes to a focus on the focal plane. With reflecting telescopes, you can have what are known as folded optical paths, meaning that the light can fold onto its over it or back onto itself. So let's start off with a Cassegrain focus. So when you go to the observatory, our telescope is a Cassegrain optical system or optical design. What that means is light comes in from the top of the tube, hits a mirror, primary mirror, which is 32 inches in our case. That light gets bounced up to a curved secondary mirror and then back down through a hole in the primary mirror, and it comes to a focus, and we have actually another mirror which reflects it to various ports. We simultaneously have cameras and eyepieces attached to the back end of the telescope, and we can direct the light to whichever one we want at any particular point. But you can see the light kind of, well, bounces um, over itself. And so that's what we mean by a folded optical path. Now, the first reflecting telescope is actually developed by Isaac Newton, hence the Newtonian focus. Newtonian focus is you have a light again coming in through the top of the tube. It comes down, hits a primary mirror, which reflects the light back up to the tube or top of the tube or near the top of the tube, which hits a flat mirror, and that redirects it off to the side. A Naismith-Coudet focus is one that uses a third mirror, where kind of similar to ours, in that it takes the light, again, bounces off a primary, hits the secondary, and then hits a flat mirror to bounce the long light off the side. Now, there are pros and cons to these particular systems, why they were developed. For example, with the Newtonian focus, again, you have the issue of the larger the objective is, or the larger the aperture, the longer the focal length. And so even though that light is being folded back onto itself, if you build a large enough refracting or reflecting Newtonian telescope, that focus is very high off the ground. And I know this from experience because I use the Newtonian, a 30-inch Newtonian telescope, and when it was pointing up in the sky, you literally had to climb up uh, probably around a 20-foot ladder in order to get up there. And me being the undergraduate, I got to be the person up on the ladder dealing with the filter wheel. So the Newtonian focus fairly quickly became inconvenient to use. And so Cassegrain design was created. The Cassegrain means that the focal plane is at the back end of the telescope, basically the bottom of the telescope. So you can imagine that when it's pointing around, the camera is still pretty low to the ground. You can still access it fairly easily. The problem with this design is that you have to cut a hole in your primary mirror, meaning that we don't actually have the light collecting area of a 32-inch telescope. We have the light collecting we have the light collecting power of a 32-inch telescope with a hole cut in the center of it. And then you have the Naismith Coudet focus. Now, the reason for this is actually, and let me see if I have kind of got cut off, but so with modern telescopes, this is the Keck 10 meter. And if you look over to the left, I don't know, I don't know if you can see my cursor at all or not, but over to the left, you kind of see this little building. Um, that is where well, sorry, over to the right, this thing over here, I think it's over to the right. In either case, you have instruments, you have cameras or spectrographs attached to the telescope, particularly with spectrographs. Spectrographs have a lot of optics in them and they have to be very, very stable. So you really don't want this thing moving around. So with a Cassegrain design, while is more convenient to access that camera, it is moving around. It moves around as the telescope moves around. So, which is not, as I said, very good for high resolution spectrographs or very sensitive spectrographs. With the Naismith focus, that focal point where it gets, where that focal point does not change relative really to uh, the angle or the altitude of the telescope. It changes as the telescope moves around in this direction. But if the telescope is moving around in this direction, it's stationary. So basically, the spectrograph or whatever instruments do not have to. We have eliminated one degree of freedom in terms of its motion. So that's the reason for that. The problem with the Naismith focus is that it uses a lot of uses three mirrors, and even though we are using optics that have a reflectivity of 99.9%, meaning that out of 1,000 photons, it reflects 999 of them. If you have multiple mirrors, that percentage drops. You are losing light as you add more and more glass. And we'll get a little bit more of that into it um, later on when we talk about spectrographs. All right. Interferometers. So um, I mentioned the angular resolution issue or the diffraction limit. The diffraction limit again is a function of diameter, but it is also a function of wavelength. So it was the radio astronomers who really were really felt this constraint early on, in that you had to build these. This is the VLA. This is the and this shows just how creative astronomers are. This is the Very Large Array, VLA. Not kidding. Each of those telescopes, each of those dishes is 125 feet across. So, from a radio telescope standpoint, they're actually fairly small. But if you array them into an interferometer, you can simulate a much larger telescope. Basically, the telescope simulates an array, an interferometer can simulate the resolution you would get from a telescope that is the size of the distance between the farthest two elements. So, for example, in its widest configuration, the distance between the two telescopes that are furthest away from each other is 24 kilometers. That is a hell of a lot longer than or larger than 125 feet. And so you can simulate a much larger telescope using interferometry than if you used a single telescope. Now, there are problems, there are difficulties with interferometers, there are severe limitations with interferometry, which I won't really get into. That really isn't the um, within the scope of this class, but if you're interested, you can always ask me offline. Um, so the radio astronomers were the ones who really developed this technique, but then as technology evolved, we have it moved into the infrared and optical regime. And so here's another example, or here's an example of a very creative acronym and a interferometer used in the infrared part of the spectrum. This is the VLTI, Very Large Telescope Interferometer. Each of those telescopes is a VLT, a very large telescope. They're 8 meters in size, each of them. And so this can simulate a telescope that is, and I don't know why we mix units, but I think this is around 180 feet, if memory serves. The interferometer I used in my research had a baseline of 331, I'm sorry, 180 meters. The telescope or the interferometer I used in California had a baseline of about 330 meters. And from that instrument, we were able to get images like this. So if you were to look at a star, a single star in a telescope, it effectively looks like a dot. It looks like a point of light. Even in the largest telescope, almost all stars will appear to be a dot. Um, so when you look at images of Hubble, you look at images of JWST, all of the stars are going to look um, like little dots with spiky spikes, diffraction spikes coming off of them. So if you're interested, like I was, in looking at the surfaces of these stars, you were up a creek. The only star that could be resolved, and that was even partially, was Betelgeuse. Betelgeuse is large enough and close enough that the Hubble telescope can actually resolve it as a disk, as opposed to a point source. And you can see that at times Betelgeuse has a bright spot on its surface, which is why people were wanting to study it. We were able to. This is a very crude sort of. Please don't summon him. I loves me some Betelgeuse, but I can't deal with him right now. um, This is a very early on image, and so there's a little bit of noise to it, but you can see that we were able to basically resolve that bright spot. But probably more dramatically, we are able to image stars like Altair. Altair rotates very, very rapidly. It rotates hundreds of kilometers per second. And so instead of a nice sphere like our sun is, it actually is oblate. It is far wider at the pole or at the equator than it is at the poles. And so stars can be flattened because of how quickly they rotate. And theoretically, we knew this in the sense that we had data which we interpreted that data could only arise from a flat object or a flattened or an oblate spheroid. So, but now we have direct evidence that these stars are shaped like this. And probably most dramatic is a friend of mine took the series of images on the right. And there is a star called Epsilon Auriga that was just a mystery for decades because every 24 years or so, I think, it would just get real dim for a few days and then brighten again. And there was and they really the best explanation they could come up with is that the star was being eclipsed by a disk, meaning the meaning that it's a binary system where you have a large red star, a large sorry, large blue star. The red in this image is arbitrary. You have a very large bright star, and then its companion is still forming and has a dusty disk around it. And that it will eclipse the star and it will do so with a disk. And he was able to actually see that disk come into frame and then move across the image. It's actually still one of the most incredible set of observations I've ever seen. And I was there when he took the data, so I'm very happy with it. So these are the types of things that you can gain from an interferometer. This is what you can gain from higher resolution, is that you can start to see, you can actually start to confirm the physical reason for why the light is behaving in a certain way when the star is unresolved or when the system is unresolved. For me, I loves me some exoplanets and young stellar objects. This was a highlight for me. Basically, we knew from Hubble space telescopes, and I will eventually get into this. When we talk about how planets form, how stars and planets form, a disk of material will form around the early star or protostar. And within that disk, you have the formation of planets. Hubble was able to uh, actually image these disks, but only in certain very specific situations. The disk had to be edge on. So you had a star, and then the disk was basically flat in your line of sight. And you can see that in the Hubble images off the left, as dark lanes, those dark bars. That is the disk as seen from the edge. Unfortunately, if the disk is not aligned so that it passes in front of the star, the disk is effectively invisible. There's not a lot of light coming from it, and so we cannot really resolve it very well, or we really can't image it very well. That was until we had ALMA, which I can't remember the acronym. This one's actually a little bit more creative. It's Amakama something microwave array. This is an array in the Amakama Desert in Chile, in the Chilean mountains, in the Andes, made up of microwave telescopes. So these are radio telescopes, but they operate in the shortest wavelengths in in radio. And they looked at a particular young star system that we highly suspected was a star with a disk around it and with the potential that planets were currently forming. And when we image it, this is what we got. This is HL Auriga, and you can see these grooves in the disk, and those are caused by the gravitational presence of the planets. So while we cannot see the actual planets themselves that are forming in the disk, we can see evidence of their presence in this disk. And so you can, with this image, there are at least five, maybe six planets that are in this system that are currently forming as we speak. The bright center, that's actually unresolved or partially resolved. So if there are any planets forming there, we may not be able to resolve the any kind of rings inside of it. So for me, very, very cool, very, very exciting. The one you've probably seen, the interferometric image you have probably seen, if you because it made the news for a little bit, were these, particularly the one on the left. Now I'm going to be that guy for a second because when these were taken, if you don't know what this is, these are images of supermassive black holes. These are black holes that are millions, if not billions of times the mass of the sun. The origins of supermassive black holes is still debated. We still don't know exactly how they formed. And so having direct images of them is very useful in answering that question. The first image was taken in Messier 87. This is a galaxy that is millions of light years away. That orange disk roughly corresponds to the size of our solar system. So it is an amazing feat that we were able to see something
How many?
so small, relatively so small, at such a large distance. Now,
Yeah.
the again, to be that guy, this is actually not an image of a black hole because technically speaking, black holes do not emit any light whatsoever. Therefore, you cannot take an image of it. However, what this is an actual image of is the material surrounding the black hole. So, what was even most notable with the
It's the
Milky Way galaxy is that with Messier, this is a very active black hole. And we'll get into that later on. But effectively, there's a lot of material there, and it's actively getting dumped into the black hole, making it extremely bright, extremely luminous. Whereas with the Milky Way galaxy, actually, thankfully for us, it's on a diet. It's really not consuming a whole lot of material at this point. So being able to see that there is still a significant amount of material around the supermassive black hole is important in that we realize that the while a galaxy is not when it is not currently getting a lot of material dumped onto it, it can still have material that is orbiting around it. And what's also very cool is um, you might think that these rings are basically face on, that you're seeing the disk face on, and actually you're seeing it at an angle to the point that the back end of the disk should not be visible because the light should fall into the black hole. the black hole itself should block that light. However, because of relativity and because light bends, we're actually at the light off that disk is actually being bent over the black hole so that we can see it. If you've seen Interstellar, you've definitely seen this animations of this sort of thing. Um, So thank you, Jacob, because I was about to actually forget how to tell you how these images were created. These images were created using a an interferometer known as the Event Horizon Telescope, because this interferometer was built essentially for one purpose, and that was to do this, to image black holes in the center of galaxies. It is an interferometer that is technically the size of the Earth. And so, for a number of reasons, I consider radio astronomy as dirty, dirty cheaters. Because one of the things that radio interferometry can do that optical interferometry cannot is you can have such an immense baseline because you have a telescope, say in Chile, a radio telescope in Chile. The Earth rotates, it sees the galaxy, takes data from it. As the Earth rotates, you have a radio telescope in Hawaii
I mean,
take data on the same object, while the Chilean telescope can no longer observe it. For the people in Chile, the galaxy is has set. And so you can take
like,
data over a long period of time from multiple telescopes and then combine that later to create these images. With optical interferometry, you can't do that. It has to be collected and combined in real time. So these telescopes were arrayed across the surface of the Earth. And so so the resolution of these images was the resolution as if you had a telescope the size of the Earth. And yes, the redness around and the color again is arbitrary. This it was just chosen to be a red palette. Since this is in the radio, it's not in the optical part of the spectrum, so we had to put a color to it, and they chose red. But yes, these are images of gas and dust that is encircling the black hole. That in the case of M87, that material is actually falling into the black hole, whereas with the Milky Way galaxy, not so much. It might have some accretion or some mass infall, but not an appreciable amount. Heard is one of the best black hole renders. A lot of time and resource to just render 8 seconds of it. Um, I don't know. I actually don't know how long it would take to render an image using EHT, an EHT data set. Having rendered my own images, I can say that it takes it takes a while. It can take quite a long time, depending on the size of your data set. All right. Now, last thing I want to talk about today, fairly quickly, is the atmosphere. I have a love-hate relationship with the atmosphere as an astronomer. I love it because, breathing is cool. Having an atmosphere, having air around me is pretty awesome. Being protected from UV light, X-rays, gamma rays is also pretty awesome. But in terms of the astronomer part of me, the atmosphere kind of sucks because I'll show you in a minute that the atmosphere can distort images to a very large extent. So, strictly speaking, in the optical, this is different for radio telescopes, and again, they cheat. For an optical telescope, what is the most ideal site in order to mitigate the effects of that atmosphere? Well, the first one is get as high up as possible, look through as little atmosphere as you possibly can. So the top of a mountain is ideal. So when you look at these telescopes, VLTI, the VLTs, Keck, these are on the tops of mountains that are 14,000, 15,000 feet high. You want something that is a site that is fairly calm in terms of wind. You do not want the that place to have a lot of chaotic wind gusts, that sort of thing. Um, and as it turns out, again, if you look at the location of these telescopes, they're generally speaking located near a large body of water and ocean. Because the reason for that is the wind that is coming off the ocean is pretty calm. It's very straight, it's fairly straight, and it's not very chaotic. And so the distortions that it causes are far less than you would see on a similar site that was more inland. You want it obviously to be dark. You do not want it in a densely populated area, um, like LA, for example. You want it to be dry. One of the major contributors to the one of the major causes of these distortions is in fact water droplets, is water vapor. So you want it to be dry in that you do not want a whole lot of humidity. And also, obviously, you can't look through clouds, at least not in the optical. Again, radio cheats. You can look, you don't want to look, you can't look through clouds, so you want as little, a few clouds as you possibly can. So let's address lighting conditions, light pollution, which is something at the observatory we're trying to actually take steps to mitigate in our area. While it is a losing battle, we're not going to get rid of the existing light. That's not something that is not a reasonable expectation. All we're trying to do is we're trying to slow the process down, slow the growth of light pollution as time goes on. Because you can see here, this is a map, and this is actually fairly dated. I think this is around the mid-aughts, um, maybe the 2010s. Somewhere in that area. So it's at least a decade old. And this is a composite satellite image of the nighttime or the nighttime sky or the nighttime Earth. Uh, and basically, this is cool for a couple of reasons. One, the not so cool aspect is you can see where the light is. There is significant light pollution because these images were taken from space, so you can actually see these street lights from orbit. So these areas are very, very bright. Kind of from an anthropological point of view, this is cool because you can see that's the areas where there are humans. So the large dark area in South America, the Amazon. Not a lot of humans in the Amazon. Middle of Africa, you have dense jungles and you have the Sahara Desert. You have deserts. Again, not a whole lot of people in those areas. So it's interesting to see, like with Australia. Australia, most of the population is basically result or constrained to the perimeter of the continent. With the United States, you can see that's roughly, the eastern half has a lot of light, the western half, not as much. It's the Mississippi River, roughly, is the dividing line because west of that is where the farmland is. So in that sense, it's pretty cool. But you can see just how bad the light pollution can be in certain areas. It is said that 90 or 80% of the population of the Earth. Um, I'll address that question at the end of the lecture. Um, 80% of the population of the Earth has never seen the Milky Way galaxy with their naked eye, which is startling to me. I have actually only seen the Milky Way galaxy 15 times. So few and so notable that I can actually remember how many times I've done it. Because you have to go to a fairly significantly dark sky to do it. In this area, the best place to see it would be the Sky Meadows State Park. Where amateur astronomers really like to go, uh, and for star parties and so forth, you can see the Milky Way there. Now, what does the atmosphere do? Well, one thing that it does, well, overall, it basically causes the star to blur out. So, twinkling. I like to say to people that if you look up in the night sky and you see something that is twinkling, that's a star. If you look at something that is not twinkling, that's a planet. If you look at something that's blinking, then it's a plane. If you look at something that is not not blinking or twinkling, but moving really, really fast, that's probably Starlink. So if you look at a star from the ground, if you're probably going to see or take an image, take a digital photograph, you're gonna get something like this. You're gonna get the star that is some kind of bright blob in the center, and then the background is probably going to be some just muddled image of brightness. And that is because the light that is passing through the atmosphere is bouncing around all of the water vapor, it's bouncing around all of the smog, and so forth. Oh, very cool. I was at the Grand Canyon once, but I was passing through and it wasn't at night. But if you go to space, this is the same image, not the same scale. It's zoomed out a little bit, but this is the same star. And so here you can definitely see a lot more detail simply because the atmosphere is not there. For example, if you looked on the left-hand image, there's kind of this cross-shaped little bright blip. If you look at this, the Hubble image, it's in the upper right because again, the images are tilted relative to each other. So now, just by getting rid of the atmosphere, we can clearly see that there is a star very close to a faint star very close to the bright star. And here it's kind of implied. You can kind of maybe sort of see it. Now, one of the things that I really wish I had taken a video of this. So, as it turns out, the telescope I used for my dissertation was actually in LA. Really, it was in the San Gabriel Mountains, which are north of Pasadena. Um, the reason for this is that interferometry actually doesn't care about light pollution. It's because of the limitations in interferometry, it can only look at bright stars anyway. So the amount of background light is actually not an issue. But it is high up, it is dry, and the wind is calm, very calm actually, because it is so close to the Pacific, which is why it's there. The reason why I'm showing you this image, and the reason why I want to take a photograph of it, or a video of it rather, is that you're high up and above something known as the marine layer. The marine layer is where all of the crud gets stuck. That's where the majority of the water vapor is. That is where the smog accumulates, just a layer of crud. When you get up, and really the peak of this mountain is around 5,500 feet, so you're not too terribly high up. When you look up the night sky, the stars really don't twinkle that much. But if you look down at the LA basin, those stars twinkle like crazy because you still have the same effect, just in reverse. So the light from the stars, light from the ground is passing up through the atmosphere and bending in the same way as the starlight that's coming down onto you. So you can see that the atmosphere here is much denser, and the atmosphere is not homogeneous. It's not the same all over the place as a function of height, and it can be very distinctive in the sense that you could have a very distinct layer even at fairly low altitudes. Now, unfortunately, it is very costly to put telescopes in space. JWST was around 10 billion. So obviously we can't do that so often. So how do we get around this? We get around the problem of the atmosphere by something known as adaptive optics. Adaptive optics is a way of effectively modeling what the atmosphere is doing to the light and then bending the mirror to do the opposite of that. So here's an example of the Cat's Eye Nebula using the Palomar Observatory, which is in Southern California. It's 5 meters in size. On the left is what the nebula, the Cat's Eye Nebula, looks like with no corrections. Basically, if you were just to slap a camera on the back end of it and take a picture of the Cat's Eye Nebula, that's what you would see. It's a very pretty image, and there is a lot of detail there, but it is blurry, particularly in comparison to when you turn on the adaptive optics system, when you turn on the mechanics that allow you to mitigate the effects of the atmosphere, you get a whole lot more detail. So on the image to the left, you have a 5 meter telescope, so your angular resolution is very tiny, or comparatively very small, but you don't get to take advantage of that because the atmosphere is blurring out the light. So if you have an adaptive optics system, you can actually get down to that diffraction limit. You can actually get down to the angular resolution dictated by the size of the telescope. One of the ways that we do this is by strapping a freaking laser to the telescope. Here is one of those. This is, I think, Gemini, might be VLT. It's an 8 meter telescope in the southern hemisphere. I know this because when I look at that image, I can see the Milky Way, and then I see um, these two blobs off to the right. Those are the large and South Magellanic Clouds. This image is a long time exposure, so it's not you would if you walked out the observatory, you would not see this with your naked eye. You can only see this really if you take a long exposure. That orange light is a sodium laser. It is a laser created by sodium gas that is in obviously the orange part of the spectrum. And so what is happening here is that is what we call an artificial guide star. We shine this laser up into the sky and it reflects off the atmosphere. And that light reflection comes back through the atmosphere and hits the telescope. We know what that light should look. We know what the form of that light looks like. We know what the wavelengths of that light looks like, and so we can compare it to the light that we actually detect, and then we can deform or change the shape of the primary mirror to do the opposite, to basically get rid of those effects. Thank you. Freaking laser beams on their foreheads. Um, that's what I was going for. So we can use that as an as a way to actually determine what the atmosphere is actually doing to the light as it passes through. This is an example of uh, that telescope when you're talking about looking at a binary system, again, without adaptive optics. That system, you really can't tell it's a binary. It just kind of looks like a big blob. But if you turn the adaptive optics system on, immediately you can see those two objects as two distinct objects. Again, I love me some planets. So if, for example, this is very important for exoplanet science. If you wanted to be able to detect or image a planet that is really, really close to its host star, you need high angular resolution in order to do it. So this is basically necessary. All right, I'm going to, let's see. Yeah, I'm basically going to finish off by talking about two hypothetical telescopes that are coming on that may or may not be coming online. So obviously, bigger is better. Right now, the largest telescopes in the world are the Keck telescopes at 10 meters. So the Americans are attempting to create, again, very inventive name, the TMT, the 30-meter telescope. The problem with this particular telescope is so the majority of our telescopes are located here. This is the top of Mauna Kea in Hawaii. So the two telescopes off to the right that looks like white balls right next to each other that seem to be connected, that is the two Keck telescopes. There are approximately 16 telescopes on top of this mountain. The issue is this site is kind of a sacred site to the Native Hawaiians. And so they've been kind of more than a little irritated that we keep putting telescopes on their sacred site. And we had regionally created an agreement that we would only have a set amount of telescopes on Mountain Peak, meaning that if we wanted to build another telescope, we had to take a telescope off. We had to deconstruct one of the telescopes and take it off. But as many agreements that are made with indigenous people, we didn't hold to that. We continued to build telescopes on the mountain, and we were proposing to put the TMT on top of it. This pissed them off enough that they actually blocked the road for a few days to the observatory. It actually got national news because Jason Momoa was actually a part of this protest, where he went and basically blocked the road to get up there to get to the telescopes. So astronomy lost actually a good number of days from our most sensitive instruments because of this. And so right now the TMT is very much in limbo because we don't. Yeah, I am actually supportive of the Native Hawaiians because there is a secondary site in the Canary Islands that we can place this telescope that isn't sacred to anybody. The site isn't as good astronomically speaking, but again, it's not going to piss anybody off. It's not that land isn't sacred to anybody. I cannot see the reason why we just don't, bite the bullet. We have adaptive optics. Just build the thing there. So right now, it's been a while since I looked into it, but the TMT is um, still very much in kind of limbo because they're looking for some place to put it. Now, the Europeans, we have a rivalry, we have a friendly rivalry with the European astronomers, European community, and so they, of course, have to one up us. And so their telescope, the EELT, or European Extremely Large Telescope, Caitlin and I agree. The European Extremely Large Telescope is hypothetically going to be a 40-meter telescope. Now, with this is still very much in the planning stages. I don't even know if they're have a definitive site. They are going to be putting it into the Andes Mountains. Here's a contrast between different peoples: is that Mauna Kea is sacred to the native Hawaiians. The Chilean people have the Andes Mountains, and they are extremely accommodating to the astronomical community. If you remember the video that, or the image I showed of the VLTs, that's very flat. Those telescopes are on a plane that is very flat. The reason for this is because the Europeans went to them, or as the story goes, the Europeans went to them and said, "Hey, we really want to build a telescope here, but we're not sure we can do it because the terrain is too rocky." And the Chileans were like, "No problem," and just dynamited the top of the mountain off of it. And so they were able to put it there. So the Europeans are not going to run into this issue. So at this point, the I am highly confident this telescope will be created at some point. Uh, but at this point, it's more of just a logistics and engineering hurdle. And then, of course, there is the problem that we are now starting to face with light pollution from satellites. But I won't really get into that, and I will end the lecture here. Next time on Thursday, we will talk about the instruments that astronomers use to actually collect the light, to measure or collect the light and so that light can later be analyzed and measured.